So this is EE619, lecture 24. Am I audible? Oh, good. So we have seen the implementation of a static D flip-flop. So you had your D here. Let's say this is clock bar. Clock. So is this a positive edge triggered flop or a negative edge triggered flop? Why is it positive edge triggered flop? So this is a negative latch, meaning you have data propagating from D to the intermediate point QM only when clock is equal to 0. And this is followed up with a positive latch. So in effect, only the data at clock is equal to a rising edge. Only the data corresponding to the rising edge of the clock will appear at the output Q. Q is going to change only corresponding to rising edges in the clock. Therefore, this is a positive edge triggered flip-flop. Now, this implementation is static in nature because all the nodes in the circuit are always being driven to either VDD or ground through an NMOS or a PMOS. Okay, so we have finished the static implementation, which means now we have to move on with the dynamic implementation of latches and flip-flops. So any suggestion on how I can implement a dynamic latch? Okay, so what should I do? You're suggesting that I take a negative latch and convert all the inverters to a dynamic inverter. Is there a better suggestion? So let me give you a circuit, analyze and tell me what is the functionality of the circuit. So I take an inverter, I follow it up with a switch, which is turning on, which is switching based on the clock signal. I'm calling this as my D, this as my Q. Can you tell me what is the functionality of the circuit? Clock into D bar. Is that right? So I want you to analyze what happens if clock is equal to 0. What is the value of Q? And if clock is equal to 1. So when clock is equal to 1, what is Q? That is equal to D bar. When clock is equal to 0, what happens to the output? It is floating or it is high impedance, which means it is going to hold the previous value. Correct? So is this a latch now? Right? If I ignore the inversion happening from D to Q, this is now a latch. Right? Is this a positive latch or a negative latch? This is a positive latch because you get the output, input reaches the output with an inversion when the clock is equal to 1. So what you have now is a positive latch. Okay. So now if I want to implement this, there are of course multiple ways in which I can implement it. The first way, of course, is to replace the switch with a transmission gate. So now if I want a positive latch, what signal should I connect here? What signal should I connect here? This should be clock, then this should be clock bar. Right? So when clock is equal to 1, NMOS is on. When clock is equal to 1, clock bar will be 0. Therefore, the PMOS is also on. So the transmission gate turns on when clock is equal to 1. Okay, so this is one implementation. A second implementation is, of course, to replace the transmission gate with a single NMOS transistor. Right? Maybe another implementation can be, what if I absorb this transmission gate into the inverter? Then what circuit can I get? So if you absorb it and make some minor variations, you get a tri-state inverter. Right? So let me remind you what a tri-state inverter is. So this is a tri-state inverter. When clock is equal to 1, NMOS is on. When clock is equal to 1, which means clock bar is equal to 0, PMOS is also on. Then functionally, this reduces down to an inverter. Right? So your output can either be 0 if your input is equal to 1. Your output can be 1 if your input is equal to 0. And if clock is equal to 0, that means that both these transistors are off. Then your output is in high impedance. So the output can take 3 states. Therefore, this is called as a tri-state inverter. Now, if I want a positive latch, what signal should I connect here? Clock or clock bar? This should be connected to clock, right? This corresponds to the same architecture I have drawn here at schematic level. So now when clock is equal to 1, this reduces down to an inverter. When clock is equal to 0, this simply opens. Okay, so these are again 2 quick transistor level implementations of a positive latch. If you think through, I'm sure you'll be able to come up with multiple other implementations. Okay, so now that you know how to implement a latch, can you go ahead and implement a dynamic flip-flop? So implement a positive edge triggered dynamic flip-flop. So let me first implement it with ideal components. So I have an inverter, a switch. This forms the first latch. Another inverter followed by the next switch. So should L1 be positive latch or a negative latch? Do you need the loop? So we saw that a single latch can be implemented like this. And if you can implement one latch, you can implement a flip-flop by cascading these two. But that's actually a very good question, right? So we have basically taken the circuit and removed the loops. What difference is it going to make? It's not static anymore. So what does that mean for us? Correct. When the switch is closed, right? When this switch is, when the switch is open, there is no path, which means there is nothing actively driving this node. And you are relying on the capacitor at this node to hold the value, right? So now in the presence of leakage, the charge stored in this capacitor can reduce, right? Which means that the voltage stored on this capacitor can now change. So now the trick is to keep recharging this capacitor, refreshing this capacitor at a rate higher than the rate at which the charge is being leaked. Which is why for dynamic circuits, you have a minimum frequency of operation constraint. So beyond that, if you are operating this at very low frequency, because of the leakages, the voltage here can change. Right? Whereas in the static implementation, as long as the data was set up and held correctly, and it reached this point correctly, right? And if VDD and ground are present, you can basically hold that value forever. Yeah, that is not true for a dynamic circuit implementation. Okay. Where? So if you remove the loop, then it becomes a dynamic implementation. Right? Any questions on this? Okay, so L1 has to be a negative latch. Your L2 has to be a positive latch. So if L1 has to be negative, what is the clock signal I should connect to the first switch? So this is clock bar. So that when clock is 0, data will reach the intermediate point, which we will call as QM. And this switch should be controlled by clock, so that when clock is 1, the QM can reach till Q. So data is reaching till QM when clock is 0. From QM to Q, it is propagating when clock is equal to 1. In effect, for the overall circuit, Q is going to change at the rising edges of the clock. Okay. Now, of course, this was the ideal implementation. Now I can implement this using a transmission gate. Or I can implement this using the tri-state inverters. Okay. Now again, think a little through and you will be able to come up with more dynamic implementations. So now we are going to analyze for these two cases. First, we'll pick up the transmission gate-based D flip-flop implementation. And then we will look for the setup, hold, and clock to Q constraints based on the delay of individual elements. This we are doing assuming zero clock skew, and that the clock edges are very sharp. There is no finite rise and fall time. Then we will bring in clock skew into picture. We'll still analyze what is happening to these flip-flops. And finally, if there is a finite rise and hold time, or if you actually had a simulation tool and you wanted to simulate and find out the setup, hold, and clock to Q propagation delay, that setup we have discussed in the last class. So the same simulation setup you can use for any of these circuits. Okay. So let's start by analyzing this circuit. Right. This is clock and clock bar. Correct, right? Okay. So can you analyze and tell me what is the setup time, the hold time, and the clock to Q propagation delay? We will call this as I1, TG1, I2, and TG2. So you have your clock edge like this. You have a clock edge. You have a data that is changing as shown here. And you expect this change to cause an edge at the output. Right? So the time before the clock edge for which the data has to be set up with your setup time, and the time after the clock edge where your data is to be held stable is your hold time. So what should be the setup time? So this should be equal to dI1 plus dTG1. So why do you say that? Correct. So before here your latch is, so here your L1 is opaque or transparent. So L1 is transparent here, L2 is opaque here. L1 is opaque, L2 is transparent. So your data should reach the QM node before L1 turns opaque. Correct? Once it is set up here, then it can easily propagate to Q in the next phase where L2 is transparent. Right? So for the data to reach here, you have to make sure the data is set up at the input for a duration of delay of this inverter plus delay of this transmission gate. Okay. So can you quickly tell me what is the clock to Q propagation delay? So this will be equal to DI2 plus delay of TG2. So if the setup time constraint is met, the data has already been set up here. Now, when the clock has a rising edge, what is the time it takes for the data to go from here till Q? That is basically delay of I2 plus delay of the transmission gate 2. What comment can you make about the hold? Safely 0, but let's get a little bit more specific. Minus? Minus I1 is still there. Then? Correct. So the hold delay, the maximum value can be negative di1 minus d of tg1. So this is actually a little tricky. We are assuming that if the switch turns off before the delay associated with it, the signal is not coming in. Right? Is this okay? So again, you think about bringing this transition closer and closer to the clock edge. Right? Now, if the data changed exactly at the clock edge, right, which means that you had to change here exactly at the time that this was turning, then your QM is not affected. Because the data has just reached here. It still has to travel through one inverter and a transmission gate for it to corrupt QM. Yeah, we have. Yeah. As soon as you get the edges in the clock, the switch is turning off is the assumption. Right? Therefore, you can afford to have a change in data actually sometime before the clock edge. It still has to travel through the inverter and the transmission gate to corrupt QM. Therefore, the whole time is negative. Okay, I can see that there are questions. Please ask. Let's take a minute to discuss this. Feel free to discuss with your partners and ask me questions if you have anything. Okay. So once the clock becomes 1, we are assuming that this turns open. So there is no point of this. Clock becomes 1. It can so the data can change even before the clock is becoming 1. Right? So let's say the data change sometime here. Right? But the date change data shouldn't appear here. That is okay. So if it starts off, it becomes open before the data crosses the transmission gate, then we are still. That is why it is here. That is why it is here. So any questions on this? Okay, so can you quickly compare the setup time we have derived here with the setup time we got for a static flip-flop? What comments can you make? This is much smaller, right? Which means you can expect that circuits you make with a dynamic flip-flop can be operated at higher frequency. Now, I'll explain that part, the relationship between the setup time value and the clock time value, probably by end of today's class. Okay. So now we will analyze the same circuit when you have clock skew, right? So I'm going to assume that you have a clock and a clock bar. Ideally, we would expect the clock bar to be like this. But let's say that there is a delay with which clock bar is being generated. Therefore, your clock bar signal is now like this. Okay, so let me draw this on the board. You have a 1-1 overlap here. Zero, zero. again 1 1 overlap. So what is the state of L1 here? So is L1 transparent or opaque here? So L1 is opaque, L2 is transparent. Here L1 is transparent, L2 is opaque. So now we will analyze this circuit during the overlap and see if some issue is going to happen in our flip-flop compared to its regular operation. And what do we mean by an issue here? We expect the output to change corresponding to a rising edge in clock alone. Corresponding to rising edge in clock, it should sample the data that has been set up and held correctly at the input. Any other change happens at the output, we have a problem, right? So that is what we want to check. So quickly tell me what is the sampling edge here and what is the non-sampling edge. So we have to look at the positive edge in the clock signal. So corresponding to the non-sampling edge, what is the overlap we have? You have a 0 0 overlap corresponding to the non-sampling edge and 1 1 overlap corresponding to the sampling edge. So now let's start with the non-sampling edge. Check if the 0 0 overlap is going to cause any issues in the flip-flop operation. Why don't you give it a try? So we are looking at the non-sampling edge. How do you define a setup time with respect to the equation is similar to which one? You have to look at a condition first. D of I1 plus, let us check that. So can you? So we are looking at the non-sampling edge and 0 0 overlap. So a good way to start this is to look at what happens before the overlap, what can happen during the overlap, and then what is the situation after the overlap. So before the 0 0 overlap, L1 is in what state? Yeah, L1 is opaque, which means a change in D is not corrupting your QM. Change in D can reach till which point? Yeah, it can reach till here, right? But it is not going to corrupt your QM. It is not going to corrupt your Q, right? So the change in data has now reached up to this point. QM is not corrupted. So during the overlap, what can happen? It has a direct path. Why? Because you have a 0 0 overlap. Wherever you have a 0 connecting to the PMOS transistor is going to turn on. Therefore, this transistor is going to turn on. This transistor is also going to turn on. So through both the PMOS transistors, you now have a direct path from D to Q. So your data can raise to Q. So the data can go all the way from D to Q. And this is sometimes called as data racing from D to Q. What happens after the overlap? L1 is transparent, L2 is opaque. Right? So now if you make sure that before L2 turns opaque, your data doesn't cross this transmission gate, then you are safe. Correct? Is this clear? If it crosses the transmission gate, then of course Q changes. If it doesn't cross the transmission gate, then your output is not getting affected in a non-sampling edge. So which means what criteria can I put on the 0-0 overlap? Has to be less than delay of TG1 plus delay of I2 plus delay of TG2. This is clear? Can you repeat the exercise for the sampling edge? So by the way, don't remember this association, sampling edge and 1-1 overlap by heart. So that can change if I assume clock bar is an advanced version of clock. So always sketch out the waveforms and determine which overlap is associated with which edge. So as before, you start out by writing what happens before the overlap. During the overlap, and finally after the overlap. So before the overlap, please look at the waveform and tell me what is the region of operation of L1? L1 is transparent, which means any change in data can reach till QM, but that is the expected behavior, right? And we make sure that data is stable for the setup time. Okay. Now, during the overlap, what can happen? There is a raise condition possible. How is that condition possible? On, and you now have a straight path between data to Q, right? So D to Q raise condition is possible. And after the overlap, so L1 is opaque and L2 is transparent, right? So now what should we do? So now this is actually a little bit tricky, right? Because at this rising edge has to reset the output current. That is a regular operation. So the overlap is happening after the rising edge. So let's say we capture the data correctly here. Any change happening in data after that should be the So we don't want an unnecessary transition in the output during this overlap period. So what can we do? So don't let it reach QM. That is correct. What is an easier thing to do here? Setup time is before the clock. So we put a hold time constraint. So we can tell the user that your hold time is some value, and internally that value is going to be greater than the 1-1 overlap. So now the user has to make sure that the input data doesn't change during this hold time. Okay. So now let us move on to the flip-flop implementation using the tri-state inverters. So can you construct a positive edge-triggered flip-flop using tri-state inverters? So this is a latch using the tri-state inverter. This latch is also called as C-square MOS latch, where C square stands for clocked CMOS. So this is C square MOS is clocked CMOS latch. So what we are now looking at is a C square MOS flip-flop. So should this be clock or clock bar? So we want this to be a negative latch and this to be a positive latch, because we are looking at a positive edge triggered flop, right? So if this has to be negative, then this should be clock and this has to be clock bar. Because when clock is equal to 0, the circuit will boil down to an inverter functionally, right? So similarly, this has to be clock bar and this should be equal to clock. So what should be the setup time? Delay of the first state inverter, right? This is the time it takes for the data to propagate from D to QM. So this is the delay of, let's say, tri-state inverter 1. What about the clock to Q delay? Delay of the tri-state inverter 2. So you can think about what the whole time should be. We will anyways now revise it based on the clock skew values present. So now we are going to analyze the flip-flop for the same skewed clocks drawn on the board. Okay, so before that, any questions on the C-square MOS FF implementation? Okay, so why don't you give it a try? Analyze for the non-sampling edge first. And feel free to discuss with your friend. So we'll first analyze for the non-sampling edge. This has a 0-0 overlap. So quickly tell me which of these transistors are on and which of these transistors are off. This one? What is the value of the clock bar here? Clock bar is 0, right? So during the overlap, this is off. What about this transistor? This is on, so no issues. What about this one? This is off. Right? And this is the circuit. So this is your circuit during the overlap. Okay. Now quickly tell me, before the overlap, what is the state of L1? L1 is opaque. Okay. Which means can QM get corrupted? Right. So QM remains steady. Now during the overlap, this is the circuit. Now if I am looking at the node QM now doesn't have a pull down path to discharge. Correct? It only has a pull up path. Which means what transition should I be looking at the input? It should be 1 to 0, right? So you can only activate the pull-up path. And to activate the pull-up path, you have to turn on this PMOS, which means the PMOS input has to now become 0. So if you have a 1 to 0 transition at the input, then you can have a change at QM. If you have a 0 to 1 transition at the input, because there is no pull-down path, QM is going to remain steady. Is that clear? So we need to analyze this only for a 1 to 0 transition. Now let's say you had a 1 to 0 transition at D, which means you can have a 0 to 1 transition at QM. What comments can you make about Q? It holds its value, right? Because again, Q doesn't have a pull down path. And your input to the second latch has now gone from 0 to 1, which means at best, the PMOS is going to simply turn off. So PMOS is turning off. There is no pull-up path. Anyways, there is no pull-down path. So Q remains the same. Is this clear? So now during the overlap, L1 is sensitive to 1 to 0 transition at D. L2 is opaque to any 0 to 1 transition at QM. So overall, there is no race condition. Is this clear? Now what happens after the overlap? After the overlap, is L2 transparent? So we are looking at the non-sampling edge, 0, 0 overlap. After the overlap, L2 is turning opaque, right? Which means the second stage is now completely shut off. Therefore, any change that has occurred at QM will not appear at Q. So during the overlap, you can possibly have a 0 to 1 transition at QM, but after the overlap, L2 is anyways becoming opaque. So this transition is not going to appear at Q. Is it clear? So overall, this circuit is now insensitive to a 0, 0 overlap associated with a non-sampling edge. Okay. So now let's repeat the whole thing again for a sampling edge. This has a 1, 1 overlap. So again, start by looking at what happens before the overlap, during the overlap, and after the overlap. So before the overlap, what happens? Before the overlap, L1 is transparent, which means you can have a transition happening at QM. Now, what sort of transition should you be analyzing? So let's say during the overlap. So during the overlap, which are the transistors that are on? Is this on or off? This is off. So let me remove. What about this? This is on. This one? Off. Why is it off? Because clock bar is 1. The PMOS gate is connected to 1. So during the overlap, this is the circuit you're dealing with. As far as QM is concerned, there is only pull down path. There is no pull up path, which means what transition should you be looking at D? You need to have a 0 to 1 transition at D. That can cause a 1 to 0 transition at QM. Can this propagate to Q? Why not? Right. So you have a 1 to 0 transmission, which 1 to 0, you have a 1 to 0 transition, which means the NMOS is now off. PMOS is on, but the PMOS doesn't have a path to Q. So therefore, a 1 to 0 transition at QM is not going to affect Q. So during the overlap, QM can have a 1 to 0 transition, but Q is not corrupted. And after the overlap, so after the overlap, your L2 becomes transparent, which means this MOS is back in the picture. Correct? And this turns on. Therefore, any change in QM can now reach the output. Therefore, during this phase, it's possible for this changed QM to reach the output. And how do we prevent that? We give a hold constraint because we are dealing with the sampling edge. So your hold time for this flop has to be greater than the T11 overlap. You can, so your T, how would you define T11 overlap? So the upper bound would be what? Should it be delay of the first state or the second state? It shouldn't reach till QM. Yeah, right. So it should be the delay of the first state. That is 1 0 is allowed. So this is now a conditional statement also. For a 0 to 1 transmission, it shouldn't disturb the QM. Okay, so far we have been dealing with dynamic latches where both clock and clock bar were involved. Can we construct a dynamic latch which uses only one phase of the clock? No clock bar. I want a latch, but I don't want to use clock bar in my circuit. I only want clock. We can have a pre-charge and evaluate type of phase. Okay, so let me give you architecture, but before that, let me give you some homework questions. So you analyze the same conditions that we have discussed now for a negative edge triggered flop. And you also analyze it when clock is the delayed version of clock bar. Okay. So again, a lot of permutations and combinations are possible. You can assume that you have a negative edge triggered flop and clock bar is generated from clock. Positive edge triggered flop, clock is generated from clock bar. So a lot of questions are possible in this case. So now let me give you a circuit. I'm going to start by taking our flip-flop and I'm simply removing these PMOS transistors. And let's say I connect both of these to clock. Can you tell me what is the functionality of this circuit? I want to know when clock is equal to 1, what is Q? And if clock is equal to 0, what is Q? So you are analyzing for clock equal to 1 or 0? Clock equal to 1. Then what happens to these transistors? Both are on, right? So effectively, this boils down to an inverter functionally. So this is also another inverter. So overall, Q will be equal to D. Right? Now, what happens when clock is equal to 0? So which node can have a transition from 0 to 1? Q can have a transition from 0 to 1. So let's analyze that, right? So when clock is equal to 0, sorry? So let's check. So let's start by looking at QM, right? So when clock is equal to 0, this transistor is not in the picture. This transistor is also not in the picture. So QM can go from 1 to 0. Why? Because it only has a pull-up path. If QM has to go from 1 to 0, what should be D? This is 0 to 1. Okay. Now, if QM is going from 1 to 0, what comments can you make about Q? Oh, no. So QM can go from 0 to 1. This can go from 1 to 0. Okay. So what comment can you make about Q? It cannot change, right? Because QM has gone from 0 to 1, which means the PMOS has now turned off. You anyways don't have a pull down path. So the value of Q will simply hold. It will hold the previous value of Q. So is this now a positive latch or a negative latch? Okay. So from the back rows there, why is this a positive latch? You can discuss and then tell me, no issues. So in 2 minutes, I'm going to call out somebody from there. So you quickly discuss and then decide on the answer. So let's say D goes from 0 to 1. Okay. So the PMOS is off, NMOS is on. QM will hold. If QM holds, Q will also hold. Q cannot do a transition. It can, but for Q to have that transition, QM should have a opposite transition. That is not possible. Okay, so last row, last end. So L1 is this a flip-flop or a latch? Why? So do you want to revise your answer? So you're calling this as a latch, is it? So the behavior we have seen for the whole circuit is this. When clock is equal to 1, output is equal to input. When clock is equal to 0, it is holding the previous value. So is this behavior that of a latch or a flip-flop? Why is this the behavior of a flip-flop? So let me give you two conditions, right? So let's say this is your data. I'm going to call this as D1, D2, D3, D4, and D5. Okay, I'm going to give you a behavior, right? So I'm going to say this is some value. Let's say this is D2, then this is D3, then this is D4, and I have D5 here. Okay. So is this behavior that of a flip-flop? So I have transitions happening at the output here when there is no edge at the output. Then again a transition here and another transition here. This is the latch, right? And what is happening here? Whenever you have a positive edge, a positive level in the clock, your D is appearing at the output as it is. Whenever the clock is 0, changes in D do not appear at the output. Okay. So is this a positive latch or a negative latch? This is a positive latch. So the same description I have given here. Whenever clock is equal to 1, Q is equal to. If clock is 0, Q is retaining the previous value. So which means this whole configuration is now, it is a latch, right? And it is a positive latch because as we can see here, when clock is equal to 1, Q is equal to D. Okay. See, if you make a mistake in the class, it's on me to explain it. You don't have to worry. Right? Okay, good. So now we have a positive latch. Can you quickly implement a negative latch using only clock as the signal? You're not allowed to use clock bar. So please implement a negative latch. So I've simply shifted the transistors onto the PMOS side. Right? So now I leave this as a homework to you to verify its functionality. Okay. So you now know how to do a positive latch. You now know how to do a negative latch. So all of this assuming that only the clock phase is available and clock bar is not available. So this kind of implementation, which uses only one clock phase, that is, it is using the single phase of the clock, is called as a true single phase clocked circuits. In short, this is called as Tspc. So what we have implemented here is a Tspc latch. Okay. So now you know how to do a Tspc negative latch, Tspc positive latch. Can you quickly construct a Tspc flip-flop which is sensitive to a positive edge in the clock? Okay. So please construct a Tspc positive edge triggered flop. There is nothing complicated here. You know how to do negative latch, positive latch. Put both of them together and you'll get it. But just to get the hang of the circuit, please draw it. So what happens if you don't have the middle stage? So you're asking why not use only the first stage, is it? So then would you have both as clock or will you have clock and clock bar? So in this analysis, when we did earlier, during clock equal to 0, we were safe because a transition here couldn't trigger a transition at the output. So now what are you doing? You are having let's say you had clock here and you were putting clock here, is it? Is this what you're doing? Okay, so let's analyze for the case when the latch is transparent. For what phase of the clock is the latch transparent? This can be a flip-flop, is it? Okay, so I know that this can't be a flip-flop because even the simpler versions have more stages. So let's analyze this after the class. So everyone can look at the suggestion given as homework and then we can discuss it in next class. But let's do this on the board after today's class. Okay. So you simply have to cascade the negative latch first and follow it up with a positive latch. So this is now the midpoint voltage. This is Q. Okay. So this is your negative latch. And this is your positive latch. And together, this is now a Tspc flip-flop. Okay. So now compared to a C-square MOS flip-flop, where you had both clock and clock bar, how many transistors are here being driven by a clock? 4. In the earlier case, how many were there? 2 for the clock and 2 for clock bar. So roughly same number of transistors, right? What about the total number of transistors? How many transistors did we have earlier? Only 4, is it? 4 per stage, right? So you had total 8 transistors, and now the total number of transistors have increased, right? But this is still a preferred configuration simply because you don't have to generate a clock and a clock bar, right? So these analysis will get much simpler. I'll tell you where this can still be a problem, right? In assuming clock at all these nodes, our first idea would be to assume that the transition is reaching at all these nodes at exact same time. But the moment you do layout, maybe the clock is reaching here slightly earlier than clock reaching here, right? But even then, the overlap period is going to be much, much smaller here compared to a clock bar situation. Okay? So now I'm going to take this configuration and make small changes to it. Right? So the first change is I'm going to replace this stage with a regular inverter. Okay. So if this is a regular inverter, I can no longer call this as a latch. If this is Q, what can I call this as? This then becomes Q bar. Okay. Now I'm going to make some change to the second stage in this latch. So the first change is I'm going to put the PMOS transistor. Instead of that PMOS, I'm going to connect it to the NMOS side, and this gets connected here. Right? And this signal is now clock, and this is clock bar. Sorry, we can't have clock bar because then it is not Tspc anymore. This is also clock. Okay. So I have taken your Tspc flip-flop. I have replaced the last stage with an inverter, and I have replaced the second stage like this. Very minor changes. Can you analyze what the circuit is doing? Right. So in particular, I want you to analyze for this case. Let's say I have a rising edge transition in clock. Okay. Let's say your data is set up much before the rising edge transition, and then it changes sometime after. So I want you to analyze how the circuit is behaving when clock is equal to 0, that corresponds to this phase, and when clock is equal to 1. So initially you can analyze it for this part of the clock phase where your data is not changing. So go ahead. Clock is equal to 0. How does the circuit behave? Let me also name every node properly. So we'll call this as node X, node Y, Q bar, and Q. So clock is equal to 0. Let us see what all transistors I can remove from the circuit, right? Is this transistor on or off? This is on, perfect. This transistor, why is it on? This is an NMOS transistor whose gate is now 0. So this transistor is off, right? This transistor on. What about this? That is also off. Okay. So let us look at only the first stage. Clock is equal to 1, which means this transistor is always on. Therefore, logically, this reduces down to an inverter. So X is always going to be D bar. Okay. What comments can you make about Y? Y is always at VDD, right? It doesn't have a pull down path. It has only a pull up path, and that transistor is always on. So this is now at VDD. So this basically is in pre-charge phase. Now if Y is equal to VDD, what comments can you make about Q bar? Q bar is floating, so it holds the previous value. So if Q bar is holding previous value, Q will be also holding the previous value. This is okay. So now let's say we have a transition and your clock has become 1. Right? And initially we are assuming that during this transition, when the clock has gone from 0 to 1, your D is not changing. Okay, we'll analyze for this situation. So we are working with the condition that the D has not changed. Let us quickly remove the transistors that have turned off. Is this transistor on or off? This is off. Why? Because you have a PMOS whose gate is now connected to VDD. So this transistor is off. What about this transistor? That is also off. This one, that is on. This one, that is also on. Okay. So what comment can you make about X? It is transparent only to 0 to 1 transition, right? Because X can have, it can only discharge through the pull down path. It can have a 1 to 0 transition. There is no pull up path available. So for X to have a discharging happening here, your NMOS needs to turn on, for which you will have to work with the 0 to 1 transition. Right? So your X is sensitive only to a 0 to 1 transition at the input. And this corresponds to X having a 1 to 0 transition. Now your Y was initially at VDD. Right? Depending on the, so right now we have assumed that our D is constant. So we don't even have to worry about this transition. Right? So your X is simply equal to D bar, which was the previous value. Okay, so now what comment can you make about Y? Y can only discharge. And when does Y discharge? When X is equal to 1. Basically, if D bar is equal to 1, then Y will become 0, which is D bar of bar, which is same as D. Correct? And if okay, so if let's look at X, right? If X was equal to 0, then what can Y become? Y will remain at VDD. And if X is equal to 1, Y will be equal to, it can go to 0, right? And given that X was complement of D, you see that Y is basically complement of that. It's basically as if you have cascaded 2 inverters. So your Y value will be equal to D. Is this clear? Okay. So what is happening is this stage is conditionally discharging. The second stage is conditionally discharging Y. This is the same concept we saw in a dynamic combinational circuit. So you have pre-charged Y to VDD, and then depending on the input, you either hold the same value or you discharge it. So during the evaluate phase, this is now implementing an inverter. Okay. And if Y is equal to D, what happens to this? Q bar is equal to? So what does this boil down to when clock is equal to 1? This is another inverter. So Q bar is simply D bar and Q is equal to D, right? So now it looks like this is acting like a flip-flop. Whatever data was stored before the rising edge of the clock is appearing at the output. All that we want to make sure now is if a transition happens away from the rising edge like this data shouldn't corrupt our output. That is what we want to analyze. Is the problem statement clear? We saw that during the rising edge, the data here is able to come to the output, but we don't want any other transition to happen at the output. Okay. So for that, we initially said that what is the transition we should consider at D? We have to look at a 0 to 1 transition, because if you have a 0 to 1 transition, then it can turn on the pull down path. Corresponding to this, you can have a 1 to 0 transition at the output. If you have a 1 to 0 transition at the output, what comments can you make about Y? Y holds, right? Because if you have a 1 to 0 transmission, NMOS transistor has now turned off, which means any change happening here will not propagate to the remaining stages. Okay? So the configuration I have given you is now only sensitive to the data around the rising edges of the clock. As long as you meet a setup time and a hold time, this will work as a flip-flop. So let me bring up the whole circuit once more. So please take a minute, discuss with your friends and see if you have any questions on this. It is sense. So what we saw was that, so we analyzed for a situation like this, right? So we saw that any data that is present at the rising edge is now able to come to the output, right? Now, when clock was equal to 0, the Q and Q bar were simply holding the previous value, right? So any changes happening at D when clock is equal to 0 doesn't come to the output, right? At the rising edge, whatever is the value set up at this state is now able to propagate all the way to the output. Right? After the rising edge, let's assume that we held the data stable during the whole time. Then any other change that happens is not able to propagate beyond this stage. You can have a 1 to 0 transition here, but it is not going to affect Y. So if I look at this whole circuit, when clock is equal to 0, this stage is simply going to act as an inverter, right? This stage is in pre-charge phase. And this is going to hold the previous value. This is also going to hold the previous value. When clock is equal to 1, what happens to this stage? This is sensitive only to rising edge, 0 to 1. This is an evaluate phase. That is, it conditionally discharges Y. This stage is like an inverter. This stage is also like an inverter. So now if you meet the whole time constraints, then this can act as a flip-flop. So any questions on this? So let us start with the setup time. So based on this, can you tell me what stage has to be set up correctly? Which of these outputs, X, Y, Q bar, Q, has to be set up correctly so that after the rising edge, the data propagates till the output? Is it Y? Y is in pre-charge phase when clock is equal to 0. Right? There is no concept of setting it up before the clock edge. Before the clock edge, it is always pre-charged to VDD. So it has to be X, right? So I'll simply write my setup time as the time taken for the data to go from D to X. Okay. Now, can you tell me the clock to Q propagation delay? This is from X to Q. Okay. So this is roughly equal to 3 inverter delay, because there are 3 stages from X to Q. The interesting part, of course, is hold. What comments can you make about the hold? So at the rising edge, we want X to reach Y correctly, right? Once X reaches Y, then we are safe. At the same time, so let's assume that the D is also roughly changing at the same time, which means I am now bringing this edge closer and closer to the clock. So if the data changes at the same time, there is a D to X path also. This is, of course, conditional change in data, right? We are not sensitive to both edges. So that is the clue. You have 2 paths. You have X to Y, the needed information going from X to Y, and the new information coming from D to X. So what should be the hold time? So basically, we need to hold the data for the duration it takes to go from X to Y, right? So this part, I can represent it as T X to Y, right? But even if we change the data at the rising edge of the clock, it takes some finite time for the new data to reach at X. Right? So that is like a buffer for us. So this has to be subtracted from this expression. So this is your hold time. So you can think about this, and if you have any questions, please ask me in the next class. And of course, one final homework. This is 24.1. Implement a negative edge triggered flip-flop in the above fashion. So this is also a Tspc dynamic flip-flop, just a different version. Sorry? Because in T-hold, right? So let's assume that the time taken for the data to come from D to X was immediate, right? Which means if the data changed at the rising edge of the clock, you can have a problem, right? Let's say data changed at the rising edge of the clock, it immediately reached here before the Y has correctly evaluated. Right? So this has been prefetched to VDD. So this should either remain at VDD or it has to discharge. So before it discharged, let's say X changed. Then it is a problem. So you want the data to go from X to Y. And if you want the previous configuration, X go to Y, then you can have that. Thank you.